Morning, everybody. Welcome, welcome. Couple of things. We have the roll sheet. Let's be fair and equal and all that kind of stuff. And start it on this side this time. Maybe you guys won't get ignored, right? But let's see if you guys can figure out how to get that back over to this side. And then I think I failed to give the 2 p.m. lab their lab packets. Did anybody in the 2 p.m. get a lab packet? No? Okay, so get a lab packet. Do I want to send these around? Sure.
As long as there's a significant enough amount.
Half of you, right? I gave it to the morning ones. All right? Make sure that if you're in the morning, don't take one, unless, right? Don't take two. Otherwise, we're going to run out. I lied, misspoke, misrepresented the truth, didn't read correctly. You guys can decide what I was doing. On one of the homework problems, the one that's got the disc with the hole cut out, where they have this and they have a point up here, and then they have another one with it cut out right here, and again right here, and like this is like case A and this is case B. I told you how to do the problem. I told you how to like treat this as two discs where this one's got the opposite charge density. You can add them together to get the whole. The way they want you to answer is weird. It says by what part does the electric field change or something like that? It's worded strangely. This is what they want you to do. Take the electric field in case A, subtract off the electric field in case B, and then divide by the electric field in case A. I think I wrote that down wrong in the 930 lab. I think I wrote EB on the bottom, okay? So just, again, to correct myself, you do this, multiply, take absolute value, you get like a percent. I think it wants you to answer as a percentage, right? Like a percent difference or a percent error, okay, between the things. What problem is this? 9, 8? I don't know the numbers, okay? But on this problem, yesterday, I didn't correct it. I didn't catch it until like 3 o'clock in the afternoon. You divide by E8, not EB. All right, so there's that correction. What else? Homework that's due this Saturday is chapter 22, right? And hopefully we got a healthy chunk of 22 kind of out of the way. We're going to talk today about arbitrary arcs of charge, which was like 2 of the middle problems, one with a semicircle, and then one with like 2 rings or something like that. So we're going to get to that right now. And I think today's the last day of chapter 22. I might even get started on chapter 23, which means that I'm ahead of my schedule, which scares me because it usually means I forgot to do something. I'll find out, because I'm never ahead of anything. All right, I'll ask that question later. Okay, so an arbitrary arc of charge. So it's easy to do like semicircles or whole circles or things like that. But I want to solve every problem for all time without having to do every single one, right? So I'm going to try and set this situation up as generically as possible. Again, in mathematics and physics, we call this arbitrary, meaning that it doesn't matter where this arc begins and ends. We should be able to apply the answer that we get to whatever situation we may have. What does that mean? All right, let's drop a coordinate system down. Got to be able to reference stuff. And then I'm gonna draw an arc. This is like that was terrible. That's not much better. Okay. So I've got this wire, this line of charge. It's a straight bar that's like bent into a circular section, okay? And all of those are supposed to be at the same radius, even if it doesn't look like it. Here's my y-axis. Here's my x-axis. And we're going to define a couple of angles here. We're going to call theta 1, like the angle where this wire begins, right? It's going to start at some angle, and then it's going to stretch through to a second angle. We'll call that one theta 2, right? So let's say that I had a situation where my arc of charge was like a quarter of a circle. What could my first angle be? Oh, okay, so I could start at 180 over here and then go to 270. That's a possibility. What if I started over here? What would my theta 1 be? 0, and theta 2 would be? Do you get the idea here? Okay. If it was a semicircle, I could go from 0 to 180, or from 90 to 270, or from 180 to 360. You getting the idea? So I can define any segment of a circle, okay, and determine the electric field at the origin by what we're going to set up here. So again, I want to try to leave my angles as generic as possible. And just because I drew this starting in the first and ending in the second doesn't mean that that's it, right? I can go anywhere, right? 0 to 360 would get me the whole circle. Okay. So that's kind of the idea of the setup here. Okay. So as we go, we're looking for the electric field at the origin. How are we going to find it? We're going to add up all the little tiny contributions of electric field from something. And since it's a line of charge, what are we going to break our line of charge up into? Little tiny segments. And those segments are going to be the electric field of a point charge, right? Just break the line up into a lot of little tiny point charges, since we know what the electric field of a point charge needs to look like. So what I've got to do here is I've got to pick, again, just a little piece. I like to just kind of draw two lines. It's like, this is my little piece. It exists between these 2 points, right? And that little piece is going to be k dq over r cubed r vector. Again, that's the electric field of a point charge, right? We've been here before. This doesn't seem any different now, right? So in order to be able to integrate, I need to figure out two things. What two things do I need to figure out? Three things. The bounds, but yeah. To get any traction in this integral, what do I need to find in that dE? I need dq and r, right? What do you want to do first? R. Pick the hard one. Okay. Where does r vector start? We'll make it green. Where does r vector always start? On the thing that's causing the electric field, right? The thing that's causing the force, the thing that causes the magnetic field. Whatever we're talking about, there's something that's making that happen, right? So what is making electric field at the origin? It's my little piece, right? It's my point charge that's sitting right here. So where does my r vector start? At that piece. Where does the r vector end? Place you're trying to measure or find out what's going on. And where are we trying to find out what's going on? The origin. So, uncomfortably, my r vector is going to start up on my arc and come down and end at the origin. Okay. So, how the heck are we going to represent this r vector based on how we're measuring things here. Let's table that one, because you look a little bit scared and confused and slightly concussed. Let's go to DQ. Let's see if DQ can kind of help inform our R vector a little bit, because they do need to kind of talk to each other, right? However we're busting this up and whatever we're going to tell the integral how to integrate, we want to make sure that that DQ and our R vector are copacetic. So let's go to DQ. And what can we use? How do we link DQ to something physical? Charge density. Linear, surface, or volume? It's linear. This is still a line of charge, right? We're not going to do arbitrary shapes in here, like squiggly lines. That can be done, but we're following nice curves here. So it's linear. That's total charge divided by total length, or a little piece of charge divided by a little piece of length. So our dq is equal to lambda dl. None of that's different. The hard part is, what the heck is dl? It has to be a little tiny portion of that arc. Arc length. We're not going to bust this up into x and y. Because if we did x and y, we'd have to have a dx dy going all the way around. And as a physicist, I cannot support multidimensional integrals. I want to do the one dimension if I can help it, right? So I will pay the price and not live in Cartesian coordinates. I will go to polar coordinates, where arc length is equal to a radius. I'm not saying this is the r vector, times an angle, right? So what does this look like? If I take a little piece of this arc, am I taking a little piece of the radius of the arc? Or am I taking a little tiny piece of the angle? It's theta, isn't it? We're going around in theta on this arc. So my d theta goes right there, right? Let me clean this up. Right, it's arc length, s equals r theta, but then we're going to take a little piece of that arc length, and that's going to be r d theta. If we broke it up in r, which way would we be telling the integral to go? Kind of like that, right? Because that would be a dr, right, going out radially like that. Instead, we're going to break this up into thetas, d thetas, right? Heading around like this. Now, let's take care of this arc length radius r and my r vector. Is anything the same about those things? Is the radius of my arc and the magnitude of my r vector the same? Yes. Now, my r vector is not pointing out along the radius, but my r vector does go from the arc to the center, right? So its direction is different than a radius vector, but the magnitude, right, no matter where it is, it's going to be the radius of this arc, isn't it? So am I safe using the symbol r here? Yeah, I don't have to worry about like making it an a or a b or a c or like some other number, right? Like it's the same thing. The radius of my r vector and the radius of my arc length are the same number. So symbolically, we can do that. Okay. So we've got our dq, right? This is going to be lambda, and then my dl is my ds, which is my r d theta. Okay. That dq is telling me how I need to write my r vector this time. What will the integral be chewing on? What will the integral be working at? thetas, right? So how do we want to write down our r vector now? What must our r vector depend on? Thetas, right? We have to get our vector written down in terms of theta because our integral is going to be in terms of theta. And does the direction that our r vector is pointing, does it change with thetas? Yeah, right? It can be vertical, it could be horizontal, depending on which angles we're at, right? So now, now we've got to write our r vector kind of cleverly here. I'm gonna come off to the side here, and I'm going to draw my r vector. Going to try to make it big, right? So it's like here's the arc, and here's my r vector, right? This r vector is at some angle theta, and that theta has to be between theta 1 and theta 2, right? Somebody said limits. What are our limits going to be? Theta 1 to theta 2, right? But so this angle has to live somewhere between those two angles. But again, I want it to be any angle in my limits. So now, how do I write down the components? The components of r. Oh, sine and cosine? Oh dear. Okay. Well, angles being what they are, alternate interior angles being what they are, is the x component. And I know this sounds weird because, like, Mr. Bay, I thought you were living in polar coordinates. But in the end, I kind of want to know what direction the electric field's pointing at the origin. Like, is it pointing in x, pointing in y, pointing in both, right? So we're going to write this down in terms of x and y components. This x component right here, sine or cosine? How is it cosine? It's touching that angle right there, right? And the y component, sine or cosine? Sine. All right. So what are those components? Well, this one is r cosine theta. Again, hypotenuse, length of hypotenuse times trig function r sine theta. But what directions are they pointing? So this is negative r cosine theta I hat minus r sine theta j hat. Why are those both negative? They both point in the negative direction, right? Negative x, negative y for how I've set up my problem here. So these aren't negative angles. These are positive angles. The negative sign goes on the I hat and the negative sign goes on the j hat. In my setup, I'm referencing every single one of my angles from the positive x-axis. Right? So what happens to this r? Let me see if I can get to the root of your question here. What happens if my angle is bigger than 90? Let's say my angle is 100 degrees. What happens when you put in the cosine of 100 in your calculator? Your calculator will spit out a negative value, won't it? Because your calculator knows that in the second quadrant, x has to be negative, right? Well, now you have a negative times a negative, and which way will your r vector be pointing? And does it, if the r vector is over here in the second quadrant, does it have a positive x-axis component? Yes, it does, right? So writing it down this way, using angles from the positive x-axis and making sure I use the actual angle from the positive x-axis, I should be safe. So let's do third quadrant. If we're all the way down in the third quadrant, r vector will point from the arc back to the origin. So it better have what? Both positive. And in the third quadrant, sine and cosine, they're both negative. Negatives wipe all this out, everything becomes positive, and I'm still consistent with the direction of my r vector. Did I answer the question, the thing you were getting at? I think so. Okay. So this way of writing down r vector, this is a great problem because not only are we going to solve all the problems for arcs, but you're seeing another way to conceive of the r vector. The R vector up to this point, we've always just kind of looked at the diagram and just gone a distance and made sure we got our directions, right? But we can also write it down in like this polar form, right? Where we're taking advantage of the angular dependence of this situation. All right, lots of tricks, and learning them all takes time. What's the magnitude of this vector? R. Why is it R? Because I said so before. It's just the radius, right? So the magnitude of our vector is just R. I don't want to prove it, but what happens if you square each of those components and add them together under a square root? You get cosine squared plus sine squared, which is 1, with an r squared factor that comes out, and the square root of r squared is? For all the mathematicians in the room, you are now satisfied. Okay. What have I got? I've got a mess. This electric field at the origin is going to be the integral of dE. What the heck is dE? It's k dq, which is lambda r d theta. Okay, I'm good with that, right? Divided by r cubed. What's the magnitude of r? R. And now I have to write down r vector, right? Minus r cosine theta I minus r sine theta j. I need limits. What are my limits? It's going to be theta 1 to theta 2. I think my notes are wrong. No, my notes are not wrong. I just can't read. Sorry. Can I clean this up? What can come out? K. Lambda. And again, in your book, K is 1 over 4 pi epsilon naught. Your book likes to write a lot of stuff, apparently. Can the d theta come out? No. Can the r come out?
Yeah, but it reduces.
Oh, it reduces? So I've got an r. I've got an r here and a factor of r that comes out, which makes this an r squared over an r cubed. So I'm just left with a 1 over r. But is r changing in this integral at all? No. Negative sign comes out. And then I think I'm left with stuff I can't deal with. This is going to be a cosine theta I plus sine theta j hats d theta. Yes. Okay. What is this right here in the box? What's in the box? It's the equation for the electric field at the origin of any arbitrary arc of charge. So I'm cheating a little bit here. I haven't solved all of them because I haven't integrated this yet, right? But if you're given an arc of charge that starts at 87 degrees and ends at 200 degrees, what do?
You plug it in for the balance and solve.
You start in the box, right? Start in the box. And why do you start in the box? Does everything in red depend on what angle we started with? No. Right? I tried to set this up as generically as possible, as arbitrarily as possible, to be able to do any angles, right, start to finish. Just make sure that your angles are always measured from the positive x-axis. None of these 4A shenanigans where we make sure all the angles are less than 90 degrees or something like that, right? This setup depends on if you're in the fourth quadrant, you better have angles bigger than 270 and less than 360, right? Okay? We're going to do the semicircle right now, okay? And I'll just do that example and then I'm going to move on with life. You might want to do the quarter circle. Because if you do a quarter circle, then that applies to every quarter circle you're going to come into contact with, right? Okay? Since we're going to do the semicircle together, the result for the semicircle will apply to any semicircle you get. And on your homework, let's see, I think you had a homework problem where there was like, was it like this arc was positive and then like this arc was negative or something? That's just two quarter circles, isn't it? So if you've solved the quarter circle version, it becomes a much faster problem. Be sure to get your directions right. If it's negatively charged, which way? Points towards the negative, right? Points away. But magnitude-wise, you'll have the answer, right? So this is what we do in physics. We try to develop tools so that we don't have to do the math anymore. Okay, so let's do, I'll just do it on this page. Semicircle. Do I have room on this page? The answer is no. All right. What do I need? I need this thing. Copy that. Isn't it fascinating to watch old people try to... Oh, there we go. Paste. So we'll stick that right up there. Okay. We're going to do the semicircle. What does a semicircle look like? We're going to go there to there. So we're going from 0 degrees to 180 degrees, right? For the semicircle. So let's see here. Can I be clever and avoid having to calculate one of these integrals? Because technically there's two integrals there, right? Two one-dimensional integrals because there's two terms. What do we know about electric fields and what all of this is going to do down here at the origin, right? Well, I'm going to have charge from over here causing like electric fields pointing that way, right? And then on this side, it's going to be electric fields pointing that way. So as I add together all of these things, what direction is going to survive? Just the negative y, isn't it? Because these directions are going to cancel. By the way, for the quarter circle, is that true? No, you're going to get both. You're going to get all of these, right? So a little bit harder, but not so bad. All right, so I'm going to make an argument. By symmetry, two words that mathematicians hate. By symmetry, all of the I components will add up to 0. Now, if we didn't catch on to the concept there, like, let's just say we're sort of going to blindly trust the math. What do you think might happen to the integral of the cosine of theta from 0 to 180? What's the integral of cosine theta? Sine theta. And what's the sine of 0? 0. And what's the sine of 180? 180. So what's that integral going to do?
0.
It's all coded in there, right? The matrix knows how it works. Okay? So the symmetry argument holds. We could prove it mathematically, but this is a physics class, not a math class, so we're just going to go with that. Okay, so what do I write down? The electric field at the origin, negative k lambda over r from 0 to 180 degrees. And I'm just going to write sine theta j hat d theta. Again, why am I not writing down the I component? I know it's going to cancel. I know it's going to go away. So let's not waste any time. Yeah. It looks like I just have a lot of math to do here. Integral of sine theta. Is it negative? I never know if it's negative or positive.
It's negative.
Great. Okay, I just stopped. I got lazy and didn't want to write 180 degrees. So pi. So this is, so can I make that, can I just cancel that?
Wait, does the j hat go away?
No, it's there. I don't, whatever. All right. I know this is going to be down when I'm done, so. All right, so let's see. K lambda over r cosine of pi minus cosine of 0. Did I do that in the right order? I think I did. What's cosine of pi? It's negative 1. What's cosine of 0? Well, it's negative 1 minus 1. Negative 2. 2k lambda. Yep. All right. What do we do about lambda? We put charge q on this semicircle. What's lambda going to be? K is a constant. R would be whatever the radius of this arc is. It's q divided by the length of the arc, isn't it? Lambda is the q divided by the arc length. What's the arc length? It's pi r, isn't it? 2 pi r divided by 2. All right, so I can write down, we'll write down 2k lambda over pi r, 2kq, substitute your things right, Mr. Balogh, 2kq over pi r squared. Oh, where did the squared come from? R and R came together, right? So it's not really an area, it's just happened to be pi r squared, okay? Times a negative j hat. Did we end up with it pointing down like we thought it would? What is the electric field magnitude at the origin for any semicircle of charge? What's the magnitude? 2kq pi r squared. What will the direction be? Depends on the charge, right? It depends on where my semicircle is, right? But I know the magnitude will always be that value, and the direction will always be either towards or away from the arc of charge, depending on whether it's positive or negative. Solved every semicircle. You can do the same for every quarter, eighth, 3/4 of a circle, whatever, right? You can always back up to the red thing, and then as long as you can integrate sine and cosine, which apparently I can't because I need to ask every time, it's a good thing integral tables exist. We're done. With that, we have come through chapter 22. Chapters 21 and 22 are, up to this point in your physics career, if you've taken 4A and 4C, chapters 21 and 22 are by far and away the hardest chapters you have ever experienced. They will be eclipsed by the magnetic field chapters. Okay? But so far, you have climbed the highest mountain. Some of you are saying, Mr. Balogh, I'm still down on the slope dying due to lack of oxygen. Come save me, right? And you have a lot more work to do to get to the summit, right? But I'm standing on the summit saying, come on, you can do it, right? You're almost there. Get that homework, get that studying. Some of you are coming to me. You're not complaining, but you have a complaint. And it's, Mr. Balogh, this is taking a whole lot longer than Physics 4A. Yes, it does, okay? Just know that you are going to get some of that time back on the next unit. Circuits doesn't take as long as this, okay? Right? So big time now, like grasp, all of you are like in grasp trying to survive, and then in circuits, I'm going to be sitting there alone, right? Because you guys just don't need that much help from me for circuits. So, and as you'll discover, you won't want my help with circuits because I make circuits explode. But just realize that you are almost there, right? And you're going to start getting over a hump. Now, what I'm going to do now is I'm going to shift into chapter 23. I'm going to take this a little bit slower than normal because chapter 23 is part of the brutal trifecta, okay? But chapter 23, the whole point of chapter 23 is to not do integrals. It's an alternative way of thinking about electric fields that on the surface looks like we're doing integrals. But in fact, in chapter 23, there's going to be a lot of integrals that you do see that you won't be doing. However, there are some integrals that you don't see that you'll end up doing. And I know that doesn't make any sense right now. But you'll see why in the end I made that statement. Let's begin. Chapter 23 is all about something called Gauss's law. And in order to help you understand what Gauss's law is doing, I need to introduce you to an idea and concept called flux. This becomes one of the cornerstones of how we understand electric fields and magnetic fields in space. Flux is going to come back, okay, in the context of magnetic fields. So it's important that we give you an idea of what flux is, and then try to start applying that. So I want to spend the better part of the rest of our time this morning together talking about flux, how it works, what it is, how we calculate it. This is a mathematical construct. Kind of like a vector is a mathematical construct, something that represents, mathematically something that has direction and magnitude. Flux is a mathematical construct that allows us to quantify or measure or determine how much field is in a given space and what that field is doing. So, let's get started. As soon as the word flux goes on the screen, what do you think of? Flux capacitors, right? Okay? From the incredible 1980s series of movies, Back to the Future. Okay? If you have not seen these movies, shame on you. You now have a homework assignment. Go watch Back to the Future. At least the first one, right? Okay? Dr. Emmett Brown, played by Christopher Lloyd, my hero. Dr. Brown, not Christopher Lloyd. But in the movie, there is this thing called a flux capacitor, and they show it right there, right? Okay. As you are about to learn, the flux capacitors is one of the most hilarious Easter eggs and nods to the science community that has been done in film. In the movie, what does the flux capacitor do? Does anybody remember? Blah, 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 technobabble, 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 right? importantly, it's the device that makes time travel possible, right? Okay? And Doc Brown describes how he was like hanging a plant in his bathroom and he fell off the stool and he hit his head. And when he woke up, he had this vision, right, of how to develop the flux capacitor. It's, of course, untrue. It's a MacGuffin in this movie for making time travel possible. And one of the things that makes Back to the Future so good is it doesn't try to explain what's going on. You're just, okay, fine, flux capacitor, go time travel. Flux is a measure of flow. It's a measure of vector flow through a surface. As you are going to learn next unit, a capacitor stores things. Capacitors in our class will store electric charge. So the flux capacitor is an oxymoron. It's a device that stores stuff that flows. The implication being time, right? And what's an oxymoron? It's two words put together that have opposite meaning, right? So jumbo shrimp is an oxymoron. Government efficiency. Military intelligence. You get the idea, right? Okay. So the flux capacitor is not real and is wrong on so many levels. But when the writers wrote it, it was a wink, wink, right, to everybody that knew what flux was and knew what a capacitor was, right? Because the flux capacitor is an oxymoron. It's cute. But that's not what flux is. What the heck is flux? So it's this measure of flow. It's this measure of how much of one thing passes through a surface. And I think maybe the best way to try to conceive of this, like just physically, before we go into the abstraction of electric fields and such, is really to go on a field trip. And just seeing pictures like this makes me happy. I know. Right? Yeah, it's just, I'd much rather be here than there than here, right? And I would love to take you on a field trip. Field physics. There's a field biology class. Let's make a field physics class, right? Where I just take you out to fields and rivers and throw you in, right? So it's a static picture, of course, but is that water going anywhere? Sure, it's flowing whatever direction it's flowing, towards us or away from us, doesn't matter. And maybe we want to measure how much water is flowing down this river per second. Like what could we measure? Like what's one way we could capture how much water is flowing in this river? Give me a unit. What? Okay, gallons per second. I'd prefer liters per second, but okay, well, America. We will do gallons per second. Okay, so how do we measure that? Like how would we determine the gallons per second? Stop the river. We'll measure the area of the cross-section. No, okay, so we can't stop the river. Unless you know Moses, there's no stopping the river. Okay? So what can we physically do to take this measurement? Put a bucket, but the problem with the bucket is it's going to stop the flow, isn't it? So what if I gave you a piece of chain link fence? Right? It's fencing that's got holes in it, right? Or poultry wire, chicken wire, whatever, right? Fencing that's got very narrow wires in it and kind of big openings, right? Okay? I handed you this piece of fencing. I said, go measure the flow of that river, that creek, right? What would you do? Got your piece of fence, okay? River is flowing from this side of the room to that side of the room. I throw you in the water with your piece of fencing. How are you going to measure the flow in the river?
the volume on the inside of the fence.
How would you hold your piece of fencing? If you held it like this and the water's going like this, does your piece of fence have any water going through it? No, right? So you would turn, right?
Wouldn't you want to hold it out like with one arm?
Oh, okay. Sure. Right? Okay. Right? Okay. But the idea here is that the orientation of your piece of fence matters, doesn't it? And to get the most flow through your piece of fencing, how would you orient it?
Against the flow. Yeah, like that. Which way is the flow though? This way? What? Not that way. Yeah, yeah, that way. Or that way. No. No. Yes. Yes. Yes.
You all struggled with how to describe the orientation of this thing. You said that? I didn't hear it. Big words are coming out now, right? We've had what so far? Oxymoron, and now we've got orthogonal. Okay? But what? Okay, we'll get to the orthogonal piece in a second. How are we measuring the flow? Like if we hold it like this, like what are we saying? We're going to measure what? The area seems to make a difference, right? Like if you have a bigger piece of fencing, will you measure more flow? Okay, so flux is dependent on the area as well as the amount of water that flows through your area, right? A bigger area will capture more water. A smaller area will capture less water, but if the flow is kind of equal all over the place, they should come out a little bit like a density, right? Smaller areas, less stuff. But like we can capture like amount of water, liters or gallons, flowing through the area per time, right? The flux isn't the per time part. The flux is the water going through the area part. What would the flux be if we held it like this? 0. There's no area being exposed to the flow, right? What's the flux if I hold it like this?
0.
Also 0. So my flux is going to go from like some maximum value to a 0 value, and any other values in between. Why? Why is the flux changing with the orientation of my area? As I face you and tilt this, do you see more or less of the area as I tilt it? It's getting less and less till it gets to 0, right? So, do you agree or disagree that the orientation matters? Definitely matters, right? So now we're to orthogonal, right? But what is what's perpendicular here? We have a flow vector going from left to right across this room. That's our creek, our river, right? Okay?
It makes a magnet triangle.
What does?
Chain link fence, whatever it's called. The plane? It's an orthogonal plane to the vector.
The plane of your area is perpendicular? Parallel to the flow? What if I please, no right-hand rules, not yet. Okay? I need to teach you something that you may not be aware of. But before I do, I want to show you the mathematical definition of flux. And I'm going to do this now in terms of the electric field. So let's get away from our water and our chain link fence, okay? And instead of the water, we will have an electric field flowing from right-hand side of the room to left-hand side of the room. Left-hand side of the room to right-hand side of the room. Knew I got it backwards, okay? Electric field lines, electric field vectors. It's the water, right? Flowing along, okay? And instead of a piece of chain link fencing, we're going to have an area, a square, a triangle, a rectangle, okay? A mathematically defined area. To find the electric flux flowing through that area, capital phi or phi, okay, the Greek letter capital phi, is our symbol for flux. Sub E, meaning electric flux, is defined as the electric field vector multiplied by the area vector. Flux is a scalar. It's a number. Electric field is a what? Scalar, vector, or elephant? Vector. It's a vector. Area. Scalar, vector, or elephant? Area is a vector. There's no cross products here. Don't go there. Dot product. Right? But to get a scalar out of two vectors in the dot product, both of them have to be vectors, right? Otherwise, it's just scalar multiplication of a vector. That's not because if we did scalar multiplication of a vector, if we did scalar multiplication of a vector right here, we would get a vector out, right? Yeah. Flux is not a vector, it's a scalar. Which means that area is a vector. How many of you were taught? What's the area of this table? How do you find the area of this tabletop? Right? You've been taught that since, I don't know, third grade. I don't know, when do they do this now? Kindergarten, preschool? Right? You find the area by just doing it. Done. If it's a triangle, I do 1/2 the base times the height. If it's a circle, I do pi r squared. Those aren't vectors. Oh, they're vectors. What direction does the area vector of this table point? It points up. The vector direction of the area is perpendicular to the surface. You find it, unfortunately, by doing cross products, okay? But you can take a vector that defines one edge of this table, another vector that defines the other side. You do the right-hand rule, and you will find the mutually perpendicular vector that defines the area, direction of the area vector. In practical terms, any area that you are given will have, how do you find the area of this binder? Right? Easy, no problem. What direction does it point? Perpendicular to the surface. Okay? Why would we do that? Why would you make area harder than, Mr. Balogh, my life is complicated. It's complicated. It's your fault. It's not my fault. You signed up for the class. It's your fault. I've got complicated personal issues and complicated physics issues, and now this is too far, right? This is just a bridge too far. Straw that broke the camel's back. Why is it important that we know the orientation of this area?
It's supposed to be exactly opposite.
Is this area the same as this area? No. Why? Orientation changed. Is this different? Is this area unique to say this area and this area and this area? Can we use area vectors to give a completely non-arbitrary definition of what the area is and the orientation of that object in space? All those triangles that they calculate in Pixar movies. Every video game that's ever been made completely depends on this vector. How is that surface oriented in 3D space? How do we know? Area vector. How many of you have been lied to up to this point? Misled? Yeah, they did, right? Lied to by omission. You didn't deserve the truth. Not till today. One time I had a student come up to me after this lecture, right? All these eye-opening definitions about area and other things. He came up to me and he grabbed me by the shoulders. He looked straight into my soul. And he said, Mr. Balogh, I feel like I have been given the talk. And I am walking out of this room a different person. And he let go and he walked in. Right? Like, I'm not your father. All right. So, area is a vector, right? And if I hold my piece of chain link fence like this, the flow vector was that way, right? To the right across the room. But my area vector is pointed which way? Opposite. And if I take the dot product between two vectors pointed in the opposite direction, I get what? Positive or negative number? Negative, right? The cosine of 180 in there, right? Because anytime you take a dot product, finish your math, Mr. Balogh, this can be found as magnitude of electric field, magnitude of area, times cosine of the angle between the two vectors. If I've got 180 degrees between my vectors, cosine of 180 is? Negative 1, 0, 50-50 chance. Okay? So if I turn and I hold my piece of fencing like this so that the area goes that way, right? Now is the dot product what? Positive, because the angle between them is 0. Now it's 0, right? My vector's pointed perpendicular to the flow direction, right? Orthogonal. 0, 0, 0, positive, negative, right? What happens if I do this? Do it this way. Then it's something in between 0 and whatever positive, right? Okay? So we can capture all of that conceptual idea we had about how much water flows through, how much area is exposed, right? In this mathematical framework of the dot product, as long as we understand that area is a vector. So it's all fine and good when you have just a piece of chain link fence and you're standing there. Mr. Balogh, what happens if you have other things like, I don't know, cubes, spheres, cylinders? You sensing a theme?
No, I didn't want to do direct.
Uh-huh. So let's start with the cube. This is the most accurate diagram you will see all semester because I can't draw. Okay? And it's not the greatest cube in the world, but you get the idea, right? Okay? So here's my cube in 3 dimensions, and let's say that I've got an electric field that is flowing. Okay, so what I should be drawing is that it goes through everywhere in space, right? But that gets messy. So we often draw the electric field off to the side, and we just kind of note it's everywhere. Okay? So that electric field is everywhere, but primarily it has one direction. What direction is it flowing? To the right, positive x direction. Okay? We want to find the flux, the total flux through the cube. How do I find, so now this is kind of like a volume, right? But flux depends on area, doesn't it? So really it's the surface area of this cube that matters. And we could try to tackle the whole thing at once, but we're not going to do it. Let's break this up into 6 different considerations. Why 6? 6 faces. This is where the drawing is going to get really messy. Okay, so we're going to find the flux, the electric flux through this cube, right? By finding the flux through each of the faces. I'm getting tired of writing this. Where am I? 5 plus 6. I got 6. So phi1, phi2, phi3, those are all talking about the different faces. Let's see. Face number 1 is the side facing us. Face number 2 is there. Face number 3, and then 4, 5, and 6 are going to be on the backs, right? So 4 is behind here, 5 is this side, and 6 is the top. You guys following my labeling here? It doesn't matter what, I'm trying to, anyway. Okay. What is the flux through face number 1? What is the electric flux through face number 1? What do you have to figure out? The angle, right? So what direction does the area of face 1 point? Kind of like towards us, right? And what angle does that make with the electric field pointing to the right? 90 degrees, doesn't it? We've got a vector pointing out and a vector that's pointing horizontally, right? It's 90 degrees between them. So what's the flux through face 1? 0. Okay. And what about face 2? What direction is the area vector on face 2? Perpendicular to the surface. It's on the side. Yeah, the 2's on, right? Okay. So the electric field vector and this area vector are pointed in the same direction. So what is that flux going to be? It's going to be E times A times the cosine of 0. Cosine of 0 is positive 1, isn't it? Okay. Flux through 3, the top. 0. Why 0? Area points perpendicular away from the surface. Y is perpendicular to x, right? E is along the x. This area is along the y. So that's 0. Face 4, the back face, opposite of 1. 0. Face 5, which is opposite of 2. What? This face, its area points opposite the direction of the electric field. So it's E times A times a negative 1 from the cosine of 180, right? And then what about face 6, the opposite of 3? I did put 6 on the wrong place. 6 is down here. 6. 0. I did that in the wrong color. So, how much flux do we have? 0. 0! I found a really complicated way of thinking about 0. Why was the flux 0? How much electric field went in? The same that went out. If I hold a cube of fencing and I want to find the flux through that cube, whatever flows in will be exactly equal to whatever flows out. And so the net flux, the total flux, would be 0. You're like, Mr. Balogh, isn't it going to be 0 no matter what? Can you conceive of a situation where the electric flux wouldn't be 0? Yeah.
Like a leakage?
A leak. Oh, so like a bucket kind of holding water, and you drill a hole in it and the water starts flowing out? Ah, okay, so what's the electrical analogy of that? Go simpler. What if we put the point charge inside of the box? Where do electric fields start? On point charges. They end on negative ones somewhere else, right? But we know what the electric field shape of this point is going to be, right? What's it going to look like? Bad hair day, right? Is there a symmetry that we can take advantage of? Do the electric fields of a point charge look like a cube? No. It's more circular. It's thinking in 2 dimensions. That's good. But we need to think in 3 dimensions. Right? These electric fields are all going out like this, aren't they? And there's a symmetry there. What symmetry exists here? Spherical symmetry. So what if we drew our area, our surface area, as the surface area of a sphere? Think of a basketball, right? What direction does the area vector for a basketball point? There's only one direction, and it's out. It's not x, it's not y, it's just radially outwards from the center, right? What direction does the electric field point if we put the charge at the center? Also out, radially outwards. All of our area, the area vector of the sphere, the area vector of our electric field, they all point in the same direction, so what's the flux? Not 0, right? It's just outwards, isn't it? Area vectors and electric field vectors all pointing in the same direction. Angle is 0, it's just E times A. And what's the area, surface area of a sphere? 4 pi r squared. Area of a cylinder. What arrangement of charge do you think we might want to use to use cylindrical symmetries? If I have a line of charge, can I draw a cylinder around it? It's like a bunch of point charges all next to each other, right? So all the field lines are just coming away from the line of charge. I could draw a cylinder around that. What's the surface area of a cylinder? 2 pi r times the length of the cylinder, right? We're going to ignore the ends. We're only going to use toilet paper rolls. Ignoring caps. The idea of flux is to encapsulate or capture the concept of vector fields. We can think of them as electric field lines passing through areas. In the case of a point charge, the bigger we make our area, the further apart those electric field lines are. If we make it smaller, then they kind of get closer together, but it's the same number of field lines that exit, right? Flux up close, flux far away, exactly identical. What we're going to do when we get together next time is I'm going to introduce you again to somebody you probably have already run across in your math classes, Carl Friedrich Gauss. If you've done anything with a Gaussian distribution, if you've done anything in math really at all, you've probably been affected by Gauss. I'm going to introduce you to Gauss again, and we are going to talk about a law that he developed that allows us to do a shortcut around really nasty integrals. This law that Gauss came up with uses this concept and idea of flux, and we will apply that next time. I will see you on Thursday. What? You like this? Okay. I want to hear that after you take the exam.